Welcome to chapter 14. This is on architectures for machine learning. So, in this chapter, we will first learn a little bit about modern contemporary machine learning, and then we will discuss modern architectures for machine learning. So, basically, AI and ML driven accelerators are very popular as of today. So, there is a need to understand the way that they are architected. So, a little bit about the background that is required. So, we need a background in order pipelines. So, that most of you have till this point. So, this is the last chapter of version one of the book. C++ programming and basic parallel programming. So, this is something that is required to understand how parallel programs are written. Because if you think about it, something as computationally heavy as ML is actually written with the help of parallel programs. So the background chapters for this chapter are chapter 6 and chapter 9. And chapter 6 and 9, so chapter 6 basically talks about GPU programming, and chapter 9 talks about multiprocessors. So this is what is needed to go further. So we will talk about five different sub chapters, five different themes in this lecture. So we'll start with basics of deep learning. Then we'll talk of the design of a convolutional network. This is important. Then we will talk about how we take a basic convolutional network and then we divide it into smaller computational units. Finally, we'll talk about optimizations and the way that we architect memory systems for machine learning accelerators. So if you think about it, this is a bespoke new processor. So both new processing as well as new memory, both are required. So let's first give a basic machine learning introduction to dummies. So the key idea is if you think of a function, any regular function, it will take a set of inputs and provide an output, or we can think it will take a vector, a column vector of inputs. So which is basically, an input with many tuples. Like for example, the input could be today's temperature, humidity, pressure, and so on, and it could just predict whether tomorrow we will have rainfall or not, right? Just a yes or no predictor. So this for us is a function. So in many cases, like let's say, if I have a function of this type, x squared plus y cube, then I know the form of the function. So I know what the function looks like. But in many cases, I don't really know the form of this function. So what I know is I know a bunch of inputs. So as I said, they could be a single variable input or they could be multivariable inputs. So I know inputs and their corresponding outputs, but I don't know the form of this function. So when would such a case be? Well, whenever we are talking of any intelligent action, like the human brain, for example, so we know the inputs that are typically given to it, and we know the output, but we don't really know the exact function that the human brain uses. So, what would be some of those advanced functionalities? Well, one would be a face recognizer. So, a face recognizer would be basically a circuit where you give it faces, it will tell you who the person is. So, our brains can do this very easily, but doing this on a machine is difficult. Same holds for speech recognition, object recognition, or even something like movie recommendation. So let's say that you know your friend's likes and dislikes. So today, if your friend comes to you and says, "Can you recommend a movie?" So you know the movies that are currently playing in theaters, so you can make a recommendation. But a machine does not know your friend as well as you do. So to make a similar quality of recommendation, again we need a very smart and intelligent function. And of course, we need past inputs and past outputs. On the basis of that, we would like to somehow figure this function out such that if a new input is given to it, you can predict the output with an acceptable level of accuracy. So what are some simple ideas? Well, a simple idea is that I look at all the input output patterns that I have. So this is also called, golden data or ground truth data. So basically this is kind of guaranteed to be correct. So in this case, I look at the inputs that I have. I look at the output. I look at the input output correlation, right? And I try to make a good guess. This is difficult. If I have few variables, I could use curve fitting. For example, let's say for several values of x, if this is the value of y, if I'm given a new value of x, let's say one that I have not seen, so let's say these are the values of x that I've seen and I do curve fitting. If I'm given a new value of x, I can predict the value of y. So this is of course a 2D curve, but I could have a 3D, 4D, 5D. I could have a multi-dimensional curve and I could use curve fitting if it is possible. So actually towards the mid 80s and the late 90s, I would say that curve fitting was by far the most dominant approach. And then, of course, more sophisticated versions of curve fitting came up, like support vector machines and so on, which actually did this. But very soon, it was realized that for very large multidimensional data, simple curve fitting is not going to work, right? If we know the form of the function, like, if we have some approximate guess whether the function is linear, nonlinear, exponential, whatever, our job will become much easier, right? To actually do a curve fit. For example, if we know that the function is of this type, then basically guessing the values of a, b, and c is easy. But if I have no clue of the function at all, then guessing that this is the form is actually very difficult. So that is why curve fitting towards the late 80s and early 90s was kind of a saturated field, and subsequently also it hasn't grown. So the question that arose, I would say, towards the early 90s is that can I have a universal approximator? So what is a universal approximator? The key idea is that, what was the key point in the previous slide, that I don't know the form of the function. So the key idea is that, okay, it's fine if you don't know the form of the function. It could be anything. But let's say I am giving you several inputs and their corresponding outputs. On the basis of that, could I have like one function which can be like some master function which can be approximated to this function? So this is a master function, right? Let's call it f master. So then what I can do is I can kind of, massage this function to actually resemble the true hidden function. Or in other words, what this means is that this function is so nicely parameterizable that its behavior is completely determined by a set of numbers. If I change the set of numbers, it will become a quadratic function. If I have a new set of numbers, it can become an exponential function. In fact, it can become any kind of function. So I'm calling this master or God function a universal approximator where its behavior is controlled by a set of numbers, and we'll call it the coefficients of the function or the parameters of the function. And basically the function is infinitely flexible in the sense that the master function can actually bend itself to resemble any real world function, right? So that would be for us a universal approximator. And for example, if there are multiple variables, it could be linear for a few, non-linear for a few more, and the universal approximator would capture all patterns which other approaches will not capture, right? So we are in search of a master function that can in essence approximate any other function. And furthermore, the behavior of the master function is controlled by a set of parameters, 100, 200, 300, 500, whatever, but a finite set of parameters. And all I need to do is I need to learn this set of parameters, which is equivalent to tailoring the master function to resemble a certain hidden function. And then the hidden function, once it is given an input, should be able to predict the output if the hidden function has been learned correctly. So what does learning mean? Learning basically means that I'm giving a set of, inputs and outputs which are known to be correct. Based on that, I'm trying to guess what is this function because I don't know what it is, right? And if my guess is correct, and I've gone by this master function route, if my guess is correct, I should get a reasonably accurate prediction for hitherto unknown inputs. Let us look at the properties of a universal approximator. So, as discussed, we have a set of multivariable inputs and a set of their corresponding outputs. So, the idea is to learn this function. But given the fact that this function is a universal approximator, its behavior is completely determined by the parameters that we give it, which means that every function is associated with possibly hundreds of parameters that uniquely determine its behavior. And the main idea of machine learning is to learn these parameters because these parameters completely control the behavior of the function. And furthermore, they should be able to approximate on theoretical concerns, based on theoretical concerns, any continuous function. So, which means that they can capture both linear, piecewise linear, and nonlinear behavior. So, let's look at the simplest approximator that we have. Again, it's not universal, but it's a learning mechanism, and we will gradually proceed towards a universal approximator by looking at more and more complex learners. So, this is an example of linear regression. So, here given an x coordinate, the aim is to predict the y coordinate. So, given the fact that our data is organized like this, so it is pretty much on a linear line, we can approximate the data as one straight line. So a general form of this equation would of course be y equal to mx plus c, but that is in a single single variable input scenario. But if I can have a multivariable input, in the sense my input itself could be a vector. So it could be a column vector. So if that is the case, this is the vector form of this. So here we have a set of weights, and the set of weights is a vector. So what I do is that I take the transpose of the column vector over here, or this matrix over here. So this is a 1 cross n matrix, and x itself is a column vector. So it's an n cross n matrix. So when I multiply both, the result that I get is actually a scalar, which is a non-vector value. It's a single value. I add that with b, which is the b is known as the bias, and then that is my predicted value of y. So what we see is that linear regression is not limited to a 2D scenario exclusively. It can be used for a multidimensional scenario as well, as in this case. So in this case, what we see is that it is basically the product of uh, you know a row matrix and a column matrix. So actually, it's a dot product if you think about it, because if I take the weight vector, which is a column vector, and then I basically compute its transpose, so it becomes a row vector. So when I multiply that with x, so what I'm doing is I'm multiplying this element with this element, this one with this one with this one. So it is pretty much like, taking two vectors and computing their dot product, right? So this is an important thing to kind of keep in mind at this stage, that we are actually computing the dot product. So after the dot product operation, we add a bias to the dot product and we get the final answer, which is y. So one important idea that we'll take along with us, so of course, along with the basic idea of linear regression, that the output is linearly related to the inputs. The other important idea that we are going to take along with us is basically that we have a dot product operation, particularly when x itself comprises of multiple variables. So we compute the dot product and add it to the bias. So now let us extend linear regression and let us look at something which is slightly more complicated. So let us look at a classification task where we have the blue dots and the red dots, or the blue points and the red points. So if you think about it, it is hard to kind of draw a linear line or a linear surface that kind of separates them. Basically, if you, as you can see, they're all mixed up, right? So it is very hard to actually draw a line that separates them. In fact, in this case, it's impossible as well. So what we do is that this is basically a 2D scenario. So we, in a sense, increase the dimensionality of each point. So at the moment, each point has two coordinates, x and y. So we increase the dimensionality of each coordinate such that, let's say we from 2 we take it to 3, which essentially means that every 2D point we convert it into a 3D point by basically calculating its z coordinate, which is not provided to us, but we'll use some formulae to compute its z coordinate and kind of project all of these coordinates to a three-dimensional space, as is in this case. So it could be that in the three-dimensional space, right, which is a projected space, we could possibly find a surface, as you are seeing, such that all the red points are below the surface and all the blue points are above the surface, right? So if this is the case, then we have a very easy way of devising a learner, which is basically that we take any point, even if a new point is given to us, as per our formula, we transform its coordinates from a 2D space to a 3D space. Then in the 3D space, we draw a separating plane, and that will separate the blue and red points. And for an unknown point, all that we need to see after the coordinate transformation is whether it is below the separating plane or above the separating plane. If it is below, we can say it is red. If it's above, it is blue, and we have a high chance of being correct, as you can see from this image over here. So basically, the idea is that this mechanism is known as the kernel trick in support vector machines, where the idea is that I deliberately make the problem more complex in the sense I increase the dimensionality of each point or the number of dimensions of each point such that I have a multidimensional space which can easily be separated out into one kind of points versus another kind of points. Right? In this case, in a 2D plane, I was not able to separate blue from red, but after increasing the dimensionality, now I can. So the other idea is that we don't explicitly compute the equation of this plane, but instead what we do is that we keep track of the points on both sides, on the blue side as well as on the red side, that are the closest to this plane, right? So basically on both sides, we just keep track of those points that are the closest to this plane. And these points are known as the support vectors. So in a certain sense, even without computing the equation of a plane, just by keeping track of the points on either side, on both sides, that are the closest to the plane, we can have a reasonably good approximation of the plane, which for our purposes is good enough. And using such support vectors, which is basically a proxy characterization of this plane, I can separate out the 2 points. And the key advantage is that if a new point is given to me, I can figure out whether it would be above this plane or below this plane, and I would make a prediction accordingly. So again, this is, by far a linear trick only, but the dimension increase part, that could be nonlinear. So there are of course a bunch of kernels that try to increase the dimensions using many different linear and nonlinear functions. So we will not discuss that part, but once the dimensions have been increased, in the higher dimensional space, again we are trying to do a linear we are trying to do a linear demarcation of both the regions, which in a certain sense is like linear regression if you think about it, quite similar, right? Of course, this is slightly more sophisticated in terms of what it does. Now, if I look at nonlinear models, which are very different from what we discussed, so incidentally, the SVMs, support vector machines, as we have seen over here, were originally proposed for nonlinear models, basically because these points could be arising out of a nonlinear process. But again, the idea was to change them to a different coordinate space, to transform them such that they are kind of linear in the new coordinate space. So this is like a semi, it's like somewhere in the middle. It's like cheating in the sense that we have our points over here, and then of course we raise the number of dimensions. And in the new space, we want it to be linear. So it's non-linear over here and linear over here. But something that is truly non-linear would look something like this. For again, we apply a linear transformation to the data, and that is to begin with. So this part is linear, and we have already seen this expression in our linear regression, right? We had the same formula. But then we apply a nonlinear function to it. And this function g is nonlinear. And there are different kinds of nonlinear functions, right? If you want to learn something whose behavior is fundamentally nonlinear, you would like to use something of this type. And for g, there are several options. So one is the sigmoid function, which used to be very, very popular in the late 90s. And the sigmoid function used to look like this with one negative exponential over here. The tan h function also is popular. I wouldn't say it's used probably as much as the sigmoid function, but again, it's reasonably popular. So in this case, what we do is that we have, a mild nonlinearity over here in the sense we have an exponential, and again, kind of a negative exponential, one on top and one on bottom. So the nonlinear function that is used most often these days is actually known as the ReLU function. ReLU stands for rectified linear unit. So we'll see what is linear and what is rectify over here. So, but first, kindly understand that both the sigmoid and tanh functions are difficult objects to handle. And the reason that they are difficult is because they use these exponential functions, which in a sense is hard to compute in hardware, right? So, which is reasonably hard to compute in hardware. This is what makes the sigmoid and tanh functions bad candidates. On the other hand, we have this beautiful function over here, which is also nonlinear, which basically says that look, if x is negative, y is 0. If x is greater than equal to 0, y is equal to x. So it's a very simple function which says that, that's the way it goes. That if x is negative, well, we stay at 0, otherwise, we go on a 45-degree line. So, needless to say, it's linear over here, and like a full wave rectifier or half wave rectifier, which cuts off the negative part. Here also, we are cutting off the negative part, hence the name ReLU, a rectified linear unit. And this, as you can see, is incredibly easy to compute. We don't have to compute any transcendental functions like e raised to power x or e raised to power minus x. We basically just need to see whether the number is positive or negative and compute the result accordingly. So that's why it is used. Simplicity is a big factor. So if I were to kind of graph all three functions, if I first let me take a look at sigmoid. So sigmoid, given the structure of sigmoid, as you can see at negative infinity, uh, the value of this would basically be 0. And at positive infinity, again the value will be equal to 1. So the sigmoid function kind of transitions from 0 to 1 and quite gradually, so basically between let's say minus 3 and plus 3, that is where basically the action happens. And otherwise the function is kind of fixed. The tanh function, on the other hand, goes from minus 1 till plus 1. So it again, most of the action happens between minus 2 and plus 2. So this is where it actually learns and adapts. ReLU, on the other hand, technically has a much bigger range. And again, but still, most of the action happens around 0 only. So here, basically, as long as x is negative, we remain at 0. And then we increase on a 45-degree trajectory. So now let's work out an example. So here the question is that we are given two Boolean inputs. The Boolean inputs are Boolean variables a and b. So we need to implement the exclusive OR function or the XOR function, which is a nonlinear function, as we shall see. So the idea over here is like this, that if let's say a is 0 and b is 0, then the output is 0. If any one of them is 1, so let's say if a is 0 and b is 1, then the output is 1. Similarly, if a is 1 and b is 0, the output is 1. However, this is where linearity breaks, that if both
A and B are 1, then the output, in this case, you would expect is 1 plus 1, but the output is actually 0. So this is why this is a nonlinear function. So if we think about it, we would need some kind of nonlinearity in our network to find or to compute the result of a XOR function. So the insights are that when A is equal to B, A minus B is the correct output. Otherwise, the correct output is the absolute value of A minus B. Why is that the case? Well, look, if A is equal to B, of course, the correct output is 0. The correct output is 0, so A minus B is fine. Otherwise, what we do is that we subtract B from A. So in one case, it is minus 1, in one case, it is plus 1. But their absolute values, right, their modulus values, both are 1. So essentially, we need to compute this function. And I can further simplify that and say, how do we compute the absolute value of x, right? How do we compute modulus of x? So if you think about it, let us go back to the functions that we have defined. Let us look at the ReLU function, which says that if x is less than 0, then the output is 0. Otherwise, if x is greater than equal to 0, the output is x. So we can simply use this. So the absolute value of x is ReLU x plus ReLU of minus x. Let us consider an example. So assume that x is positive, right? So this is a general case for all positive numbers. So in this case, ReLU x will basically be equal to x because x is positive, and ReLU of minus x will be 0. So the result is x, which is the same as the absolute value of x. Now consider the case of x is 0, that is trivial. Consider the case when x is negative. In that case, ReLU of x will be 0, but ReLU of minus x will be actually minus of a negative number, which is a positive number. That will again be the absolute value of x. So as you can see, ReLU x plus ReLU of minus x, right? Uh, Both together, they cover both the cases. And in this case, basically both the cases essentially tell us that the result is the absolute value of x. So now let us look at the network. So as you can see, the truth table is over here, that if A is equal to 0, B is equal to 0, then the output is 0. If both are equal to 1, the output is basically a 1. The output is basically a 0. So as you can see over here, A is 1, B is 1, the output is a 0. And then, as I said, if one is 0, the other is 1, the output is a 1. And A minus B, these are the values. Hence, we want to compute this quantity over here. So this quantity over here, as you can see, if A and B are equal, then it will lead to 0. Otherwise, it will give you the correct answer. So what we can do is that we have figured out that this quantity over here is ReLU of x plus ReLU of minus x. So what we do is we take A and B. Then what we do is we compute A minus B, and we compute minus of A minus B, which is B minus A. So then we compute ReLU of A minus B and ReLU of B minus A. See, if you look at this, this is a linear layer because we are computing a linear function over A and B. And these two are nonlinear units, they are ReLU units. So this is our nonlinear layer. And finally, what do we do is that we perform this addition over here. And after performing this addition over here, we get the final output. So we have a linear layer, a nonlinear layer, and a linear layer. So we shall see that this is a standard feature of all networks where we have linear, nonlinear, linear, right? And the nonlinear layer is quite essential because otherwise we would not have been able to do it. And this is our simple three-layer network, which basically computes the result of A XOR, which basically computes the function A XOR B, right? A XOR B. So there are many things that we can learn. So of course, some may argue that A XOR B is too simple. So why have such a thing? Well, my argument basically would be that if you think about it, here what we are doing is that we are taking the vector AB, right, which is a 1 cross 2 vector, one row, two columns, and we are multiplying that with another vector. So it's actually a matrix of the form 1 minus 1. So this is giving us A minus B. And so we can say that the weights over here are 1 and minus 1. Similarly, we can say the weights over here are minus 1 and 1. Then what we do is that we take it through this ReLU process, and then we can compute the XOR, right? So basically we'll have two ReLU units over here. So what is the advantage of this network? Well, the advantage of the network can be understood like this. So what we can do is that you'll find it is very easy to actually convert this to an AND gate. And of course, we could do more complex things, but even what you would see, that is, if I simply take A by B and multiply it with half and half, only when both of them are 1 will the sum be equal to 1. Otherwise, the sum will be equal to half, or less than that. And then I can multiply this with half and half, and I can multiply this with 0 and 0. And basically what would happen is that the final output will either be 0, half, or 1. So what we can do is that, well, there are other ways of solving this and making the half equal to 0, right? I mean, setting this over here, but we can just say that we will look at the most significant bit after the decimal point, and if that is 1, we will interpret the output to be 1, otherwise we'll interpret it to be a 0, which basically means that this becomes equal to an AND gate, that only when A and B are 1, then what will happen is the final output will be 1, otherwise we will interpret the final output to be a 0. So what you see is that in this general network, just by changing some of these parameters, so these parameters incidentally are known as weights. So just by changing them, we could change the behavior of the network, and from a XOR network we could make it an from a XOR gate we could make it an AND gate. And of course, as you can see, implementing an OR gate and other things are not very hard at all. And so this is kind of a generic structure, even though it can be made more generic by basically also adding a bias term, where what you do is that you multiply this AB vector with another vector over here, and you add a bias term to it. So that would make the thing more generic. And then we can capture many more functions. But the idea is very clear. The idea is that just with these coefficients, and these coefficients are known as weights. So with the weights over here and the bias over here, we can realize a variety of functions. The network does not have to be changed. So what are the key insights? The key insight is that we made kind of a pseudo generic network where it was necessary to sandwich a nonlinear layer between two linear layers. And kindly note that in many such networks, you can have consecutive nonlinear layers. That is perfectly possible, as we shall see. But you never have two consecutive linear layers, because the thing is that two consecutive linear layers are equivalent to a single linear layer. All right. So there is no difference between them. The two consecutive linear layers are equivalent to just a single linear layer. And hence you never have that. So you basically have a linear layer, a bunch of nonlinear layers, then a linear layer, a bunch of nonlinear layers, so on and so forth. So of course we could have many of these layers, one after the other, as you have seen over here. So in this case, we say that this is a deep neural network, and we have a large number of layers, and we have these parameters, which are these numbers, which we have also referred to as weights and biases in the past. So parameter is basically a combination of these weights and biases, essentially all the constants, all the numbers that determine the behavior of the network, as we just saw. So it's the weights plus the biases, right? So bias is a constant bias. So something like y equal to mx plus c. So in this case, we are saying that m is the weight and c is the bias. So basically, these are the parameters of the neural network, which if you change, the behavior will change. And deeper and more complex is the network, the more you can, the more expressive is the network. So the idea of a deep feed forward neural network is like this, where the inputs come, of course, at the leftmost point. Then basically they are processed. Some more processing happens, some more, some more, some more, and some more. So there's a feed forward network because there are no backward connections and there are no skip connections. But of course, in sophisticated networks, you could have skip connections like this, or you could have backward connections like this. So we could have hundreds of such layers, linear and nonlinear, with a bunch of skip connections as well as back edges. So training and inferencing in a DNN is like this. So what is training? So let's understand the idea of training. So DNN is a deep neural network. Training basically means that you design the network. So you basically say that, look, I will have these many layers. This is the size of each layer. These many parameters will be there in each layer, so on and so forth. That's the architecture. But the idea is you don't know what the value of the parameters is. So what you do is that you give an input. So assume that you have a set of known input output pairs. So you give an input, you measure the output that is coming and compare that with the ideal output. And based on the distance between them, you train the parameters inside the network. Once you do it for possibly hundreds or thousands or millions of input output pairs, where again, this is golden data. It's also called ground truth data, where the output corresponds to the input, right? So it's also called ground truth data, as I'm just saying. So in that case, your parameters will adapt such that the error, also called the loss function, is minimized. So of course, such large networks can be used for all kinds of things. They can be used for face detection, speech recognition, movie recommendation, finding credit card frauds, so on and so forth. So to train such a neural network, we would need the golden data, and that is why there are a lot of people who are called mechanical Turks. The idea of a mechanical Turk is basically to generate such golden data, right? It could be a human being or it could be an automated agent, and then that is provided to a neural network, and that uses the classic back propagation algorithm to basically adjust all the weights biases, adjust all the parameters such that the output of the neural network is as close to the golden output as possible. And then what happens is that at runtime, you don't know the output, of course, but you know the input. So you give it the input, it will provide the predicted output. So basically, the idea is that the better a neural network is trained, the more accurate is the predicted output. So why are neural networks hot now? If you think about it, so AI is a classic case where it has seen a lot of highs and lows, and there have been what are called several AI winters, which basically means when the field didn't make much progress. So the basic mathematics as such was developed at least 2 decades ago, in the sense that even when I was doing my undergraduate studies, which was in the late 90s, early 2000s, the maths of neural networks was reasonably well developed. But the area caught traction after 2016. So the idea was that the maths is there, but we didn't have the hardware, right? So you need several things. The first is you need the hardware. Second is you need the data, right? So basically you need massive amounts of data, and you also need the market, in the sense that who is going to produce so much of data and who's going to use your insight. So pretty much all three did not exist, but towards the last half of the 2010-20 decade, there were a lot of GPUs, fast FPGA boards, high performance computing facilities, where AI operations, which are these machine learning, training, inference operations, could be done quickly. Furthermore, there were improvements in the memory technology and off chip storage technology. And as I just said, large data sets didn't exist, but then they gradually came. Where did they come from? So consider the case of Twitter. You have lots and lots of tweets. For Google, you have a lot of search results. For Facebook, you have a lot of user actions. So basically, you can learn. You can learn that, look, if I'm interested in beauty products, you suggest some products to me. If I'm interested in, let's say, travel, you suggest travel products to me. So this learning was done, and that is how many of the large social media companies kind of came into prominence. And that was mainly because they were relying on such automated models. And of course, there is a market need now. Hence, neural networks, at least as of today, and today I'm recording this video in 2022, neural networks are quite popular. So let's now come to CNN. So CNN's, at least by far, again, as of 2022, recording this video, convolutional neural networks. So that is the C in the CNN, which is convolutional. These are the most popular. So let us define a few basic terminologies. So how exactly it works and how to design the hardware is something we will predominantly look at in the next lecture. But let's at least look at the basic terminology over here. So what happens is that let us define a basic functional unit or an FU. So I'll describe the exact inner workings of an FU in subsequent slides. So let us define an input feature map or an IF map. The IF map is nothing but input feature map. It is typically a 2D matrix, but it could be 1D in the case of, let's say, speech, or it could be 3D as well. So that is the input to a functional unit, and basically a layer comprises multiple functional units, right? So a typical linear or nonlinear layer would comprise multiple FUs. So in each FU, you would have multiple IF maps as input and one OF map, which is an output feature map, as the output. So think of it in the case of a typical 2D case, in the case of, let's say, images, you would have multiple images or 2D maps, 2D matrices as inputs, and one 2D matrix as the output. The output feature map or OF map would be the output of a functional unit. Furthermore, a layer has multiple functional units. So as I said, a single linear layer or nonlinear layer, whatever it may be, will have multiple functional units. Each functional unit will take several IF maps as input, as you are able to see over here, and generate an output OF map, which will again be something similar in the sense, if we are having 1D vectors, the output will be a 1D vector. If they are 2D matrices, the output will be a 2D matrix. Because this primarily came out of the imaging subfield, each entry of the IF map or OF map is called a pixel. Furthermore, what kind of layers are we going to have? Well, we can have several kinds of layers, right? A combination of linear and nonlinear. So the nonlinear layers are like this. So we have already seen one though. We have seen the ReLU layer. So that's the reason I have it at the bottom. But the other nonlinear layer that I would like to talk about is the pooling layer. So in this case, what you do is that you try to adjust for minor translational deficiencies in the image, in the sense if this is a face, and let's say the face is slightly translated a few pixels, or if let's say the face is slightly magnified or slightly compressed, so you try to compensate for that. So this is where a pooling layer is used. So what we do is we divide the IF map, we kind of coarsen it into groups of k cross k pixels, right? So if let's say this is a matrix over here, and then I divide it like this, then I take k cross k pixels, and for each group I compute the maximum. So that is max pooling. Or what I can do is I can compute the average, so that would be average pooling. So those are the two most common, maximum and average. So what you will see is that even if there are small, small shifts in the image, the maximum as well as the average will roughly be the same. So coarsening an image out in a certain sense does help for a little bit of error tolerance. Then what we do is we set the corresponding pixel in the OF map with the maximum value in the case of max pooling, or we would use average pooling. So the idea over here is that if we take kind of k cross k pixels and say that they are 1, so let's say we will then have a smaller matrix which is k square times smaller. It's a smaller matrix. And of course, this shape over here would still be, visible in somewhat of an approximate form, right? But the idea is that the key features will still remain. And also, if there are small translational shifts in the image or the little bit of expansion contraction, we can kind of compensate for that. So that would be the advantage of pooling, and the advantage of ReLU you have already seen, which is to provide a degree of non-linearity. So now that we have seen two nonlinear layers, namely the ReLU layer and the pooling layer, so we are now kind of done with that part. So now we have to discuss the linear layers. So the linear layers you have seen, if I go back to this point over here, you will be able to see the linear layers. So in this case, what we do is that we have a product of AB and 1 and minus 1, right? So this is a linear multiplication, so to speak, right? So it's a multiplication of a column vector and a column vector. So of course, it is the transpose of one with the other. So we can also say it's a product of 1 minus 1 with AB. So in this case, we can say that if this is the weight vector and if this is the input, then basically we are computing weight transpose. So why transpose? Because weight is a column vector and we are transposing it to a row vector. So this is a transpose of the weight vector and we are multiplying that with x, right? So that is what we are doing. Furthermore, we could add a bias term. So this is exactly what we do in the fully connected network. So what we do is that we assume that there is a fully connected layer or an FC layer, which as you can see computes a linear function. So in comes an input x. So the input, could be anything. It could be a 1D matrix, 2D matrix, 3D matrix, it could be anything. But in general, what we do is that we linearize it, which basically means that even if it's a 3D, 4D structure, we just linearize it and we convert it to a column vector. So the x that comes here, regardless of its format, is converted to a column vector. Then what we do is we do this element by element multiplication and addition, like a dot product. So we have a weight vector. So if this has, let's say, n elements, we have a weight vector whose transpose would look like this. This would again have elements, and this would be multiplied with the column vector x, where x again, each of these entries would have n elements. So we multiply them pairwise. So this is nothing but computing a dot product. So what is a dot product? It's basically pairwise multiplication and addition. This is exactly what we are doing over here. This is weight transpose. This is a column vector becomes a row vector that's being multiplied with x, pairwise multiplication and addition. And finally, we are adding a bias term. So this could be done for the pixels of one IF map or could be done for multiple IF maps with their own separate weight vectors. And then we could add the results. So this again is a possibility. But whatever be the case, the key point is that look, for a large amount of data, which is what you would expect in a CNN, if let's say X is very large, if let's say X is 1 megabyte, right? So nowadays it's also in hundreds of gigabytes, but let's say it's 1 megabyte. Then W also has to be roughly the same size, right? And if the data representation is the same, it'll again be 1 megabyte. So we are essentially doubling the storage space, right? So that's the point that in terms of computational requirements, which means we are doubling the storage space, which means we need more memory, we need more fetching, more prefetching, and we are essentially dealing with a much larger quantity See, as it is, X, which is the input to the FC layer, was large enough. So we were not happy with that. But now the point is that our array of weights is going to be as large as X, such that we can compute an element by element, pairwise product and add them. So the storage requirements are straight cut doubling. And for us, this is a substantial overhead, which is not something that we want. So what will happen is that if you have millions of weights, then the number of weights in W will be equal to the number of inputs X over here, which is not something that we like. But again, that's said and done. To compute a pure linear transformation of all the inputs, we will have to do something of this type. Now, the key point is that in a regular CNN, we have many, many layers, but we can't afford many such FC layers, primarily because the storage requirements, the memory requirements, and the prefetching requirements to ensure good performance will be huge, right? So that is why we would typically have one FC layer, because as you can see, the FC layer is exactly what we had in the XOR gate example. So we had exactly the same layer, a layer of the same type, and we were deriving a lot of advantage from it. So here also we'll do a dot product, but we can't afford many such layers because of the storage issue that I just talked about. Hence, the FC layer is typically the last layer in a CNN, and it is typically used to compute the final output. Where you take in multiple IF maps, you compute this expression over here, add the bias terms and everything. And then, the idea is that for each one of them, you have a linear transformation of this kind, and then you add the results, or you could merge the results in some other way, that doesn't matter. And finally, you come up with a single integer or a single floating point value, which is the value that your neural network is predicting. So the FC layer, as you can see, is a pure linear transformation on the lines of what we have seen. So let me write it. But as I said, the overheads are quite high. And again, the basic operation is this operation, which is a dot product plus a bias, adding a bias term. Hence, we have the convolutional layer, which is the C in the CNN. And this is by far one of the biggest inventions in this latest, uh, wave of AI ML, where people have said that, look, we can't have many FC layers; they're too heavy. So we need a computationally efficient approximation. So what you do is that basically in this equation over here, the bias term is a small scalar value. You don't care about it anyway. The input is something you can't change. The weights need not be as large as the input. So let us replace these complicated weights with a simple filter or kernel function, which is nothing but a small matrix, typically 3 cross 3, 5 cross 5, 7 cross 7, something of that nature, odd number by odd number. So I'll explain the reason why. So in image processing, that kind of comes out, but we will discuss it slightly later. But the idea is that instead of this big weight vector or matrix, whatever it may be, but for this formulation, it's a vector. What you do is that you replace it with this ultra small filter or kernel matrix, which let's say is just 5 cross 5 elements. Each kernel is used to detect a specific feature. For example, if you are trying to detect an edge in an image, what you can do is that if you slide the kernel like this in this direction, we'll again discuss what sliding means. You will see that detecting an edge is very easy. And so, what is it that we do exactly? So, what we do is that we compute a matrix dot product. So, matrix dot product is similar to a vector dot product. So, assume that this is the large matrix X. In this case, it's a 2D matrix. And we place the kernel, which is a smaller matrix, at a certain point, right? So let's say this point is, let's call it x1, y1. Little bit of confusion because we have x, but we'll resolve that later. But the point is that we take a point in the input matrix. So let's call it the IF map, right? Instead of X, let's call it the input feature map. And in that, at point X1, Y1, I place the small kernel. Let's assume it has 5 cross 5 elements. So what I do is that basically I compute a pairwise product between the one element in the kernel. So let's say this element in the kernel and element that is just below it in the original matrix, in the IF map matrix, input feature map matrix. And similarly, I compute pairwise dot products for each point on the kernel. And I'll have 25 such dot products. I add them up, and that is the value for the X1, Y1 pixel. So don't worry if you don't fully understand it, we'll revisit this thing several times. But the point is that for those who can understand it, let's say that there is an image where you're blue over here and you're black on this side. If I have my kernel over here, I'll compute a certain dot product. If I have my kernel over here, I'll compute a certain dot product. And clearly, as it's making the transition, the dot product will change. Based on that, I can infer the presence of an edge, right? So the point is that whenever you're trying to classify the image of an animal, you would first try to find out smaller features like corners and rims and edges and so on first, and then gradually combine the smaller features into slightly bigger features like horns, ears, teeth, etc. And keep combining them more and more and more into larger features in later layers until at the end you could have one large fully connected network and make a decision. For example, you can say that look, this is a kangaroo, that is a cow, and that's a goat, and so on, because essentially you have a multiplicity of layers. Each layer is learning a simple concept. You have many, many such layers. Each of them is learning a simple concept. Different layers are combining the concepts to learn a bigger concept. So on and so forth. Ultimately, you will be able to figure out what kind of animal is this. And what is really helping you? What is really helping you is this convolution operation. Where if you just go back over here, let me just clear off the clutter. That's important. Our key issue with the fully connected layer was that X was too large. And unfortunately, the weight matrix had to have, or the weight vector had to have the same size. We didn't want that, so we went for an ultra small kernel. And we found out that an ultra small kernel or filter, both mean the same in this case, is reasonably good in the sense you can find edges and so on. And then, furthermore, if you have many, many such layers, you can learn complex concepts towards the end. For example, this looks like a kangaroo, that looks like a giraffe. So, what is the basic idea of the convolution operation again? So, let's consider an input feature map with H stands for height, rows, and W stands for width, columns. Consider a point small h, small w. So, this is the coordinate of this point. So, I overlay the kernel over here, where the kernel has R rows and S columns. So, just overlay the kernel over here. Then what I do is I compute an output feature map or OF map, where what I'm doing is that in a sense I'm convolving the filter with the IF map. So now the question is why the name convolution? Well, the reason the name convolution comes is that this is similar to the classical convolution operation, but then you would argue that that looks very different in the sense, that is more like the integral of fx g y minus x, right? How is this not looking the same? Well, they are actually the same, and you need to look at the book to understand, why are they actually the same. So that part I will not cover here. But again, the key idea here is basically that we are overlaying the kernel over the point hw, and in the OF map, the value of the hwth pixel is essentially the convolution of, so in this case the 3 cross 3 kernel is the convolution of this 3 cross 3 range with the filter. So for this, what do we do? Well, we compute 9 pairwise products, in the sense this value of the filter and this value of the IF map pixel underneath it, so on and so forth. We add them and this becomes the final result. So what we are doing is that for each position HW, we are computing a matrix dot product, right? A pairwise product and sum. And we are setting the HW8 pixel in the OF map, right? So this is being done kind of as a proxy for the fully connected network. And the reason is that number one, the fully connected network has lots and lots of weights. Storage is an issue, computation is an issue, but also, just figuring out the right values of the weights using a training process, that also is very difficult. So it increases our training time and overhead substantially. So now that we have seen the convolution block, right, and the fact that we have seen how it works as a proxy for the fully connected network, we can just go back to this diagram over here, where what we have said, sorry, for the diagram for an FU, yeah, that multiple input feature maps come in, some operations are done, and a single OF map is generated. And in a layer, we have multiple such FUs. So if you kind of go back to that slide, so this is what you will have in a convolutional FU, where let's say that there are capital C. Well, C is comes for channel, but we'll discuss what is a channel later. But if there are capital C IF maps, then for each my IF map, we convolve it with its corresponding filter. So IF map I, filter I, IF map C, filter C. So then we'll have multiple convolution results, which means multiple OF maps. All of them are added. Again, how are they added? They are added pairwise or element wise. Once they are added, the output feature map comes, which is the output feature map of a FU, of a functional unit. All right. Sorry, it should be of an FU, right? So then the idea is that we just add the individual OF maps that are produced, add them element wise, and we come at the output OF map. So as you can see, the issue is that multiple convolutions have to be computed with different input, different IF maps. Each one of them is called an input channel. So we're assuming that there are C input channels, in the sense the previous layer has actually produced 5 output feature maps, which are 5 input feature maps for this layer. So C is 5. For a single output feature map that we compute, we'll have to consider all the input feature maps that the previous layer has computed. Again, this is a very important concept, so let me repeat that. Assume that you have one layer, right, the ith layer, that is producing 5 output feature maps, right? So C equal to 5 for the I plus 1th. And the I plus 1th layer could be producing maybe, let's say, 3 output feature maps, right? Where each one of them could be a 1D vector, a 2D matrix, or a 3D matrix. So then for each one of them, we have, for each one of the OF maps, we have a dedicated functional unit. The functional unit will have 5 inputs, so the 5 inputs are the 5 channels each. Then there will be one filter each. So for the ith input, there will be a filter. A filter and the kernel are being used interchangeably over here, which is a small matrix. We'll compute the convolution again for all the C input channels, all the 5 input channels will compute the convolution. We will add them, and then basically we will arrive at the final OF map, which is essentially this guy over here, the result of this point. So let's look at a short discussion. The filter, of course, remains the same for a single convolution. It is typically quite small, 3 cross 3, 5 cross 5, 7 cross 7. Furthermore, convolution operations for different OF map pixels are mutually independent. So as you can see, if I have this large IF map, then whether I'm computing the convolution in this zone or in that zone, it should not matter. Of course, there is an issue that if, let's say, this is my IF map, then at the right and bottom edges, right, which is basically at this region, there will be issues. Why will there be issues? The issues will be there because the kernel would be looking at some pixels, but some of it will overlap with regions that are beyond the OF map, right? So essentially with this region. So what we can do is that this additional region at the right and the bottom, we could pad them with zeros. So this is known as zero padding at the right and bottom edges to ensure that our mathematical operations still make sense. All right. So if I come to the summary of what we discussed, right, and we did discuss a lot though, a lot in terms of machine learning, a lot in terms of network design. So what we said is that look, in a typical CNN, it is a feed forward network where the layers are organized as a linked list, one after the other, so on and so forth. The original inputs are fed into the leftmost layer, and then we have linear layers as well as nonlinear layers. And the final output is typically an integer, which is a classification label. We never have two linear layers one after the other because that would make little sense. Because two linear layers one after the other would actually turn out to be one linear layer. The fully connected FC layer is quite computationally heavy. All right, so that we have discussed. That is heavy because the number of weights has to be equal to the size of the input. And also, the other reason is that, just training the neural network to find all of these inputs such that, the error is minimized, that is also a big task. In fact, many may want to argue that, the storage and memory cost is not much, but just the cost of finding out so many of these, weights, right? Just the cost of finding them out with the training process is very hard because you need a lot of training examples. And even if you do have them somehow, finishing the training process will take a long, long time. So the idea is to replace the heavy FC layer with a lighter version known as the convolution layer. The convolution layer is also a linear layer, but it is much lighter and it's much easier to learn. And the FC layer could still be there, maybe like one in the network, and it could be the last layer. So what we have seen in our experiments is that even in a 30-40 layer network, roughly 10 to 15% of the time, which is disproportionately large, is taken by the single FC layer, which is there at the end. So this is like a white elephant, and you would not want to have many of these, right? So this is the architecture of a typical CNN. So again, the problem, if I were to break it down for a single convolutional layer, so again, here there is a point. So why am I focusing on convolutional layers exclusively when I have the ReLU layer, I have the pooling layer, and of course I have the plain old FC layer. So let's maybe answer this first because when we move forward, you will actually be ignoring the rest of these three layers. So the first answer is quite simple. The ReLU layer is very easy to compute. So there is actually nothing. All that we have to do is figure out if a given value, if it is negative or not. So how would we figure out if it's negative or not? Well, we'll take a look at the sign bit. If it's negative, we'll replace it with a zero. Otherwise, we'll let it be. The same is true for the pooling layer. We take a bunch of values and then we basically replace them with their maximum or average. Again, that's easy. Fully connected, the hardware is easy to build. No big surprises over there. The only issue is that it is a nightmare when it comes to training and also a nightmare when it comes to storage and memory space and so on. That's the reason we'll not have many of these, maybe one or two in a large network. That's it. What we will have and what actually would determine the performance of the network will be the convolutional layer because we'll have many of these, right? And in each layer, we will have multiple functional units. So let's assume that in a convolutional layer there are C input channels or C inputs. So all of these inputs will be sent to all the functional units. For example, FU1, the inputs will be all the C input channels. FUK, the inputs will be all the C input channels. Of course, what would happen? So, what would each FU do? Each FU would basically compute a convolution between an IF map and a filter, right? So, basically, if you come to an FU, it will basically compute the convolution between an IF map filter pair and then basically add them up. So, basically, we can say that for an FU, if it is the ith FU, right? And so, sorry, let's say if it's the ith FU map and if it is the jth output map, then we will basically use the ijth filter. So basically for every input if map and of map pair, we'll have a unique filter or a unique kernel. So let me explain this in a different way. So let us assume that we have C input channels. And as I said, the convolutional layer, it is basically taking in C input channels and producing K output channels or KOF maps, right? So that is its input, C inputs and K outputs. Internally, you will have basically K functional units where each functional unit will take as an input all the input channels. Then what it would do is it would basically do this. And as I said, the filter will have many filters. We'll quickly compute how many. But the filter will be a function of the IF map and it will be a function of the output map that is being computed. So let us say that there are CIF maps and capital CIF maps and capital KOF maps. Then the total number of filters that we'll have is C times K, because as I said, a filter is a unique combination or is determined by unique combination of the IF map and OF map. For each IF map OF map pair, we'll have a unique filter. And the convolutional layer as a whole will take in CIF maps, capital CIF maps as input and produce capital KOF maps as output. All right, so that is exactly what it's going to do. So now the important point over here is basically that, well, how do we design this? So designing this is not difficult. We need to design each functional unit, and each functional unit, what it would do, it would basically compute an OF map, and then we can combine all of them into a layer. Or maybe we can treat the entire layer as one unit and design, kind of a large neural network processor to implement all of these functional units, because there's a fair amount of parallelism in the computation as well. So we will kind of leave the reader or the viewer of this video at this point. Then in the next video of this lecture series, we'll begin from here. But the key point is that we have C inputs, K outputs, right? We have CK filters, one for each IF map, OF map pair. And the key computation that is happening is this that you're seeing on the screen. So what we'll do now is that we'll discuss the design of a CNN and discuss the parallelism that is available. And then we will move on to optimizations and finally, how do you design a memory system to sustain the computational and memory bandwidth of a CNN accelerator, because the processing that is done is not something that a general purpose processor can handle. You need a dedicated application specific processor, or which is also called a neural processor or neuromorphic processor, many names, but a neural processor is required.